Hello, everyone. Very good evening, guys. Can you hear me? Could you please confirm? Okay. Yeah. Yeah. Extremely sorry for the delay, guys. There were some technical problems. I could not join. Yeah, Mukesh. Can you stop sharing the screen? Right. So today we are going to discuss about neural networks. Yeah. Let us get started. So today we are going to understand. So what are the neural networks? And also we are going to discuss about uh, the back propagation method, which is very, very important when it comes to neural networks. And we're also going to uh, understand the mathematical aspects of the back propagation as well. So that is what agenda for today. Yeah. The artificial neural network, it models the relationship between the set of input signals and an output signal. Okay? So that is what actually any machine learning algorithm does, right? So if you talk about any machine learning algorithm, be it a decision tree or SVM or whatever it is, what it does, it finds the relationship between the set of input signals with the output signal. So that is nothing but y is equal to f of x. So this is my the hypothesis means the model. So the mapping between the input signals to the output signal. That is what any model does. Now coming to this neural network, how it the neural network maps this relationship between the input signals to the output signal is using a model derived from our understanding of how biological brain works, how human brain works, how human brain responds to the signals that receives, and how the information gets processed inside a brain. That is a biological brain. So if you see the biological brain, it receives signals from various sensory inputs like our eyes, nose, ears, tongue, the skin, right? So these are the different sensors as humans we have. The inputs, so the brain receives from these sensors, it processes and it gives us the information. For example, when you're hearing, when you're seeing something on the screen, so that means the inputs are getting received and these inputs are getting processed inside your brain. So the brain, excuse me, just give me a minute. So if you see the human brain is made up of 80 to 100 billion neurons, 100 billion guys, and it is a huge and massive network. It can hold tremendous amount of knowledge. And if you compare the number of neurons with other the pets and other animals, cat has roughly 750 million neurons. Mouse has 75 million neurons, and the cockroach has roughly a million neurons. A poor cockroach. And it is actually the intelligence mostly depends on how many number of neurons one race has, and also how strongly these neurons are interconnected. It's not that the race or humans have these many number of neurons, but also how strongly these neurons are interconnected. That defines the intelligence of a race or a person. Now coming to our artificial neural network. So here also we are going to build the artificial neurons, and we are going to connect with each other, and we are going to teach how to identify the patterns from the data and how to learn the patterns from the data. So that is what the artificial neural network is. Let us see that. So if you see the neuron structure, the biological neuron structure. So this is one neuron. So like this, we'll have 80 to 100 billion neurons. Yeah, I'm sure. So you must have come across this kind of a structure in your 10th class or no, the other classes. So in biology, right? So this is one neuron, and you see the spikes kind of a structure, right? So these are called as dendrites, and this is cell body are called as soma. The information so that cell receives through these dendrites, that would get accumulated in the cell body here. And once the accumulated information, the input signals passes a threshold limit, then the signal gets fired through axon like this. Yeah. So I hope you can hear me properly. All right. Hello, can you hear me now properly? Okay, great. Right. So the signals so that receives from various dendrites, those signals will get accumulated in the cell body, and then so the accumulated information that crosses a threshold value, then the signal gets fired through axon, and then that information reaches to another cell through these dendrites. And again, so here the information gets received from another cells, the neurons, and the information again gets processed here. So again, this sends the fired signals through axon through the terminal of this neuron. So that's how the information gets processed inside our biological brain. And similar to that, if you see the artificial neuron, okay, if you see this artificial neuron here, so this is the artificial neuron. The neuron we would denote with a circle like this. And when you hear or when you see a neuron, artificial neuron, the artificial neuron has got two jobs to do. Okay? So one is the summation, the other one is activation function. Let us understand what are these. So if you see here, this is a cell or a neuron. The inputs, so we'll send it to this neuron like through dendrites, yeah, through dendrites, and each input will be associated with weights W1, W2, W3 like this. Then the values get accumulated in this. So this is basically summation. And this information, so it passes through an activation function. Then this activation function processes information, sends as output of this neuron. Now, if you see here, the summation. So how we can sum it up the entire thing in a mathematical form, mathematical equation. Now let us focus on here. So what information we are receiving here? The information x1 into w1, x1 w1 plus x2 w2 plus x3 w3. So this is summation. So at this place, so we have accumulated so all this information. Then let us write it in a short form. So since we have x1 w1 x2 w2, right? So let me use sigma xi wi. So I equal to 1 to n. How many number of input signals we have, input variables we have? So those are here. Now once I have this information I'm sending through a function, activation function. Okay. So that means, so f of sigma xi wi. Then I'm going to get the output from here. So this is how actually we can summarize whatever the neuron is doing. This is what actually you can see. The function, activation function, it processes the accumulated signals that we have received at the neuron, and then we'll get the output. This is how the neuron is mapping the input signals with the output signals. Now let us take a numerical values here. Let us try to understand here. Okay. So for example here, okay, 0.7, the x1 is nothing but the input variable. So w1 is, let us say 0, this is 1 and this is 2. Let's say for example this 2 and this half. So at this, so let us multiply this 0.7 into 0 plus 1 into 2 plus 2 into half. So this would be 2 plus 1, that is 3. Okay. So at this place, so the summation is 3. Now what is this activation function? So I can define activation function like this. The output of this activation function is 1 as long as my input values, okay, are greater than or equal to 0. And output of this is 0 for all other values. So that is nothing but x is less than 0. So this is the definition of this activation function. So this activation function should act according to this definition. Now, so this 3 is more than 0. That is what actually input value. More than 0, then what? It should deliver 1. The activation function delivers 1. Then, so if it is negative value, let's for example, then the output would be 0. Okay. So that's how actually, yeah. So that's how the neuron would deliver the output. And this is the structure of the neuron. Whenever you see a neuron, the neuron has to do these two jobs: summation as well as activation function. Now let us see what are these activation functions. So activation function is this. So we have different activation functions: sigmoid, tanh. So sigmoid is nothing but we have seen this the logistic regression 1 by 1 plus e power minus x. Tanh, a ReLU, linear rectifier. So that is nothing but max of 0 comma x. That means as long as the input values are less than 0, okay, so less than 0, then we'll give the output would be 0. So as long as the input values are 0 here, less than 0, then we'll give 0. So the moment it crosses 0, then the value would be the same as x. Whatever the input value that is there, the output also the same. So that is linear rectifier. So this is LU, exponential linear rectifier. So this is leaky ReLU, max out. We have different activation functions are there. Right? Now, the primitive or the building block of neural network is perceptron. Okay, perceptron. So before that, we had actually something called as a neuron. So that is called as MP neuron. Okay, MP neuron. So this MP neuron is basically uh, Pitts. So these two people, these two guys have invented this MP neuron, which is a very basic structure of the neural network. A single neuron. It takes uh, the binary inputs and it gives us the binary output. Okay. A little more advanced version of that MP neuron, Pitts neuron, is perceptron. And the definition of perceptron is basically like this. So I have a neuron here, and these are the inputs, X, Y. These are the weights, associated weights, AB. And then if the input values are AX plus BY, okay, AX plus BY is greater than certain threshold value, that is C, then the output would be 1. If the summation is less than or equal to certain threshold value C, then the output would be 0. Output would be 0. So that's how actually, yeah. So that's how this perceptron would work. Okay, so this is a basic building block of a neural network. Now, let us see whether this perceptron can solve some of the existing problems, well-known problems like AND gate, OR gate, NOT gate. So what do you mean by AND gate? So I have x1, x2. This is my y. Y is nothing but x1 into x2. Okay, so that is what the AND gate, right? So 0, 0, y is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So you can think of this is a class. Okay, these are the two variables, input variables, and this is my class. And how many classes are there here? Two classes. So that is 0 class and 1 class. And this is what my AND gate is. Okay, 0 into 0, 0, 1 into 1, 1, 1, 0 into 1. So all other values are 0. Now, so let us use a perceptron. When you use a perceptron here, I will get one decision boundary, one line, a straight line like this. Now use this decision boundary to form the pure region. So now these are the class, right? These are the feature space and 0, 0, 0 and 1. I have to divide this feature space such that the regions are pure regions. And with this one single line, I can comfortably so divide this feature space into two regions. So like this, if it is a two class problem, and this is a pure region, this is also pure region. And similarly, R gate also. So here also I can comfortably divide this into two regions. So this is a pure region, this is also pure region. Good. So far, so good. Now coming to a little complex problem here. So XR gate. Now, using this single decision boundary, can we divide this into two regions, two pure regions? So let's say, for example, you use a line like this, a decision boundary. Yes, this is a pure region, but what about this? This is not a pure region. Let us divide here. Yes, this is a pure region, but this is not a pure region. So that means if you use a single neuron, I'll get a single decision boundary. So with this, I cannot form the pure regions for this kind of complex problems. But can we divide this data feature space into pure region if I had two lines, two decision boundaries like this, for example, here and here? Yes, so these are pure region, these are pure region, these are also pure region. So that means if I use two perceptrons like this, then probably I can divide these and I can form the pure regions. And if you have much more complex problems, that means I can use multiple perceptrons like this and I can divide this entire feature space into pure regions. So that gives us the idea of feed-forward neural networks. That means combine multiple perceptrons in a meaningful way so that solves complex problems. This is feed-forward neural network wherein you will use multiple neurons here. Right? So these these neurons, stack of neurons, so is basically called as input layer, layer 0 or input layer. So each spherical structure here, the circle is a neuron. When you say neuron, what does that mean? Neuron has two functions. So that is summation and activation function. So whatever the values that receives, it has to sum it up, then send it to through the activation function. Activation function, according to definition of this activation function, so it processes the information, it gives us the output. That is what this same thing. And this is a layer 1, layer 2, layer 3, and this is my output layer, output the neurons. Okay, so this whatever the neurons, the neurons are the layers that are between input layer and output layer is called as hidden layer. These three layers are called as hidden layers, and each one is neuron. And also the structure here, if you see the connections between these neurons, the layer to layer the connection will happen. That means whatever the neuron that we have here, so the connection goes from this neuron to all the neurons in the next layer. And the neuron from here, it receives the connections from all the neurons from the previous layer, adjacent layer. And there is no connection between these like this. There is no connection between the neurons within the same layer. That is not allowed. And this is called as feed forward neural network. Okay. Now, what's so special? Yeah. What is so special about this neural network or the feed forward neural network. Let us say I have data like this, two classes. Okay, right. So this outer is a plus positive class and this is negative class. Now I want to classify this data. That means I want to form the pure regions. So how do you do that? This is a complex data, right? So the single linear, the model or linear line. So we cannot form the pure regions if you think this is a feature space. Now let us see how we can form the pure regions when we use the feed forward neural network. So here we are using four neurons. That means we'll get the four lines. Four lines. Now with these four lines, I can divide these like this. So inside a box, so we have negative class. Outside box, we have positive class. So like that, when you have the more and more neurons, you can solve much more complex problems using this neural network. Okay. All right. So few questions. Yeah, we'll answer those questions in a moment. Yeah, we'll answer those questions. Just have taken an example of linear. Need not be a linear. Yeah. Right. So now let us discuss about, yeah, much more deeper into this. So what are the purpose of these layers? So how do we identify these layers? Let us discuss about that. Just give me a minute. Right. So the most advanced version of the multi-layer perceptron MLP is backpropagation method. Okay, backpropagation method. So what is this backpropagation method? So if you see the earlier method, feed forward neural network. What is the feed forward neural network? So where we have the neurons here. Okay. The information flows from left to right. That means whatever the variable information that we are passing, so that information passes from left to right. That is called as feed forward neural network. Okay. Now we are going to discuss about the most useful, most popular method in the neural network, that is back propagation. So when you say you are building the neural network, artificial neural network, by default we are using this back propagation method. So let us understand this MLP, the multi-layer perceptron. That means so multiple layers of the perceptrons we are using with a back propagation method. Now let us understand this. Okay. So let us consider a simple network, a neural network like this. So we have, so I1 is the input variable and I2 is another input variable, second variable. And here we have two neurons in one hidden layer, and these are the outputs, output 1 and output 2. And if you see here, these are the weights, A1, W1, W2 like this. So if you recall our discussion, so each input would associate with a weight A and B. Right? So here we have W1, W2 like this. We have, these are the weights associated with each of these edges or connections. Right? Now this is a bias. You can think of bias. So in case of linear, so it is intercept. Okay, how to adjust that line, or in case of the sigmoid function. Okay, so where it should be. So whether it should be here, or it should be here, or it should be here. So that the placing so would be decided with this bias. So that is what actually here in this nonlinear or sigmoid functions here. Now, so what we are doing is, so let us take A numerical example. Let us work through with this example, and with that we are going to understand what is this backpropagation all about. So this is my network. Okay. So this network, so we have a data set like this. The data set is so I1, I2, O1, output 1, output 2. So when I send so 0.05, that is the input 1 to the network, I should get at output 0.01. 0.01. Of course, I2 also plays a role there, 0.10. The output should be 0.99. This is my data set. That means when I send these two inputs through this network, as the output, I should get these values. So 0.01, 0.99. So that is what actually we are expecting. And here we have the weights. So W1 is 0.15, 0.20 like this. Now, so what is the basic idea about when you say we are building the neural network or we are training a neural network? What actually the neural network is trying to learn? Given these arbitrary inputs or outputs, it doesn't know about these inputs or outputs. What it does is it finds out a function, a complex function that maps these outputs with these inputs. The parameters for the complex functions are these weights. And it's a parameters, the coefficients you can say. That means the neural network is trying to learn these weights, and when you use these weights in the network, so then the input values that you give, I'll get the output values. No matter what, how many number of input variables you have, how many number of the neurons that you are going to use. So the job of the neural network is just learn these weights and give you the output. So that is matching or exactly matching or with some accuracy with the actual or original output that you have here. So that is what the neural network training means. So training means nothing but the learn the weights, okay, learning the weights, and these weights would take the responsibility of mapping the input values to output values. Okay, all right. Now, the forward pass. So this is basically called the feed forward network. That is what actually forward pass we are trying to understand. So this is my data. Okay. Now let us work through this example and let us see what would be the output at these nodes. Right. So first, so let us focus on this H1. As we discussed, H1 has summation of the activation function. So how many inputs we are receiving at H1? The inputs we are receiving here, so 1, 2, and 3. This is bias. So let me write it down here. The inputs from I1 I'm receiving multiplied with the weight 1 plus I2 W2. Then the bias. So the bias is nothing but 1 into B1. Let us plug these values. So we have values. So 0.05. What is the W1 value? 0.15 plus 0.20 into I2. I2 is 0.10. 0.10 into 0.20 plus. So the B1 is 0.35. 1 into 0.35, that is 0.35. So this is the net input that we're receiving at H1. So that's what you can see here. So H1, net H1 is W1 I1 plus W2 I2 plus B1. Okay. Right. So this is what the net input that we are that we have received at H1. That is a sigma 0.3775. Now here we have an activation function. So here the activation function we are using is the sigmoid. Sigmoid is nothing but 1 by 1 plus e power minus x. Okay, so this is what actually we have seen. So in our logistic regression, right? Oops, excuse me. Now this value, we will pass it through this sigmoid activation function. That means in place of minus x here, we'll place this value. So 1 by 1 place e power minus 0.3775. Then this is the value that I've got, 0.593. So this 0.593 so would be sending to this 0.59, 0.59. So these values would get multiplied so with this weight, and that would receive to the O1. And again, this value would get multiplied with the W7, so receives at O2 end. Okay, so that is the next step. So similarly, I can also compute the H2, the net value at H2. So that means, so I1 into W3, I2 into W4, and then bias 0.35. So once I receive, then I send it through the activation function. Activation function transforms the input value through this logistic function. This is net out2, that is 0.596. 0.596. Yeah, so that means we have successfully completed the values at this H1. So H1, the out, H1 out is basically this is H1 out and this H2 out. Now let us compute it. Okay, thank you. Right. So now let us compute at O1. Okay, what is the value that we are receiving at this O1, and when you send it through this activation function, what would be the value here? So the same logic we can apply. So 0.40 into whatever the output of H1, that is 0.593. Then so we are receiving another input from H2. So that is 0.596 into W6. Then B2 0.60. That is what you can see here. That value is 1.10. So this 1.10, we send it through this activation function here. So that activation function again, the logistic, the logistic or logit function. So that would be 0.751. Similarly, I can compute at this O2 also, that would be 0.772. So we have successfully completed a forward pass. At this forward pass, I have got the output here 0.75, and this is 0.77. But what is the actual output here? The actual value that we supposed to get is 0.01. And we're supposed to get 0.99. The difference between these is called as error. Alright? Error. Now let us see that. Compute. Right. So the error we are going to compute with this formula. Okay. So error total is equal to half target minus output. Target is the actual value. Output means the predicted value using this network. And when you plug here for the E01, E01 means here, E01. So we have received, so we have predicted 0.75 at this node. And here we have predicted 0.77, I guess. 0.77 we have predicted here. Now, the target is nothing but 0.01, this value. The actual value, the output is 0.75. Square it. The error at E01, this node is 0.27. Yeah. The error at this node is 0.02. The same formula will apply by taking these two values. Then sum it up. So the error at first node, error at second node, the output nodes, then that total error is 0.298 or zero point 0.3. This is the total error that we have received from this network. Now, what we should do now? See, we are expecting a network, so that should give us the accurate output as close, so as close as possible to these actual outputs. But we have got this much error, 0.3 error. The next activity, the next is, so how we have to think how we can reduce this error. To what extent we should reduce? If the error is 0, then that is good for us. That means this network is accurate. That means the network is going to give us the accurate values or reliable predictions. Now our focus is on to reduce this error to zero. If not zero, whatever the possible value that we could reduce, let us go ahead and reduce it. So how we can reduce it? Now what we are going to do is, so this error we are going to send back to the network. Send back to the network. And we are informing the network, hey, this is the error, zero point 0.3 is error. Do something and reduce this error. That is what actually we are letting know this network. Sending back this error to the network is called as backpropagation. The backpropagation. What is the backpropagation? We are backpropagating this error to the network, and network does something. We'll discuss what it does to reduce this error, and in the next iteration, the error is going to be reduced. Now let us understand what network is going to do. See, we are saying that hey, this error has to be reduced. Now, if you see the structure, what is the hands of the network? What is in the control of the network to reduce this error? So we have input values, we have the weights, so we have activation function, okay, and we have nodes here, and we have output here. These are the components that are involved in computing the output as well as computing the error. Now, what is in the control of the network? See, obviously inputs. No, it's not in control of the network. We are giving the inputs. And outputs also, yes, we are the data decides. We are giving the outputs. So the inputs and outputs cannot be changed because so these are fixed values. Then activation function also doesn't control under control of network. These we are deciding as a data scientist, we are deciding the activation functions. Now, what is in control of network? Weights. These weights are in the control of the network. Now the network has to play with these weights such that whatever the output values that we have, so the network should predict exactly the same as the output values of the data set. Now the network, what it does is it takes this error, it identifies the best weights so that this error is reduced to zero or the minimum possible. Exactly, the weights, right, minimum possible. Now let us see how the network identifies so how to reduce the weights and what weight should be reduced. Now let us discuss about that. So I hope so far so clear. Great. Now, so now our objective is to find out, so how we can reduce this error, okay, by adjusting these weights. So if you want to adjust the weights, you should know actually so how much this W5 is contributing to into this error. So how much W6 is responsible so in this error. So how much, what proportion this W5 is contributing to this error. Meaning if I change this W5, so how much amount of this error is going to be changed? If I change this W1, how much amount of error is going to be changed? What is that? If I change W5, so how much the error is going to be changed? That means at what rate this error is going to be changed. So with respect to W5, at what rate? So how do we denote that at what rate? The change, the rate of change, that is nothing but derivatives. Derivatives are nothing but rate of change. So how much this error is going to be reduced or changed when you wiggle W5 a little bit. If I change W5, what is the effect of W5 on this error? That's what I want to find out. If I know that, with that amount, we are going to adjust this weight. If I know that at what rate this error is going to be changed, the same amount, I'm going to change this W5 with some learning rate. So like that, we are going to find out. So at what rate the W6 is affecting your error, at what rate W7 and all other weights are affecting your error. Then I'll take that rate of change, then I'll include in the optimization algorithm of gradient descent that we'll discuss in a moment. Right. So a few questions. I'll take all these questions, then I'll answer it in the end. Yeah. So these are relevant questions, very good questions. I'll answer those questions. Yeah. Right. So now, so how do we denote that rate of change? The rate of change we are going to denote like this. Is a partial derivative of dou E total by dou W5. That means, so if you change W5 a little bit, so what is the effect of this change in the W5 on the total error? That's what we are going to find out. Now, if you see here, from this W5, so there is no direct relationship on this total error. So in between, so this neuron is there. In this neuron, we have sigmoid here, and here we have activation function. And then after output of this neuron, so we are combining these two, okay, these two, then I'm getting this total error. That means, so W5 is not directly impacting your error, it is indirectly impacting your error. In between, there are many other systems are there. Now, let us work back through this and let us identify what are the different systems or components that are there in between W5 and the error. Let us see that now. So just pay attention here, guys. So if you see, let us focus on this part. Let us zoom into this. Okay. So the E total, error total, we have got 0.293. So that is the summation of E01 and E02, this and this. And E01, how did we compute E01? That is half target minus output of at this node. The target is 0.01. The output we have received some some 7 or something like that we have received. So that is actually we have computed. The target you can't do anything, right? So target you can't do anything. That is the actual value. So the out, this is what actually has got affected with this W5. Now, how did we get this out 01? Out 01 we have got from the net 01. Net 01, so is a component, so is summation of W5, W6 and B2. Now you see the relationship, the chain linking, right? W5 is affecting your net 01, that is summation. This net 01 in turn is affecting output because there is activation function, and this net 01 so passes through this activation function. Then I'm going to get this net out 01. Out 01 is being used in the error computation, and this error I'm going to use in the total error. So this is a chain link. Now, in order to identify, so how much amount of error is going to be changed when you change W5, then you have to link all of these, the components in this path, all of this in this path. How do you do that? The rate of change. So, in nutshell, what I'm trying to say here is, if I change W5, what is the effect on this net 01? Because it is not again direct, right? So the net 01 is a combination of B2, W6 and W5. So if you say that, hey, W5, if I change one, so net 01 also would change by one. No, it's not like that, because so the other components also involved here. First, I have to identify, so how much change that we would realize if we change W5 a little bit in the net 01. First, I have to find out that. Then I'll find out what is the rate of change of out 01 with respect to net 01, because this changes here. Because of change in the W0 out 01, what is the change in the E01? Because out 01 is being used in this E01. Because of the E01, how much it is changing? It is a straightforward method. Now we are going to uh, use all of these internal components to find out the rate of change of E total with respect to W5. So that we can accomplish using chain rule from the derivatives. Chain rule. What is chain rule? I have, let's say, for example, two systems. This is X. So this is Z. This is Y. I want to find out the rate of change of Y with respect to X. That means if I wiggle X a little bit, if I change X a little bit, what is the effect on Y? So I can write like this. So dy by dx. If I change a little bit of x, what is the change in the y? That is what actually I want to find out. So that we can find out using this chain rule. So if I change x, what is the immediate effect of the next system, that is z? So that means if I change x, there would be a change in the z. If I change x, there would be change in the z. So that I can accomplish, I can compute like this. So that is dz by dx. So what is the change in the z when you change x? Now, because there is a change in the z, that would in turn changes your y. So that we can capture dy by dz. That is change in the y with respect to z. So this is called as chain rule. This is called as chain rule. Now the same chain rule we are going to use in this method. Now I want to find out the dE total with respect to D5. That is dou E total by dou W5. Now in order to find out, so the total is getting affected by this out 01. So that is dou E total by dou out 1. This out 1 is getting affected with this net 1. That is dou out 1 by dou net 01. This net 01 is getting affected by this W5. Dou net 01 by dou W5. So this equation is a chain rule, and if you solve this, okay, then I'll get the net effect or rate of change of the dou E total by dou W5. Right? So that is what actually we are going to solve now. Right. Right. So this is what actually we're trying to solve, a chain rule, and so we want to identify the error, okay, the rate of change in the error with respect to W5. So these are the components we have to compute. Dou E total by dou out 1. So error total, okay, E total is E01 plus E02, right? E02. What is E01? This is my E01 and this is my E02. Apply the partial derivative with respect to out 01, because this is what actually I want to find out. So when you apply partial derivative on this, so I'll get this. Okay, then finally I have got this. A negative target minus out 01. So I know what is target 01. I know what is out 01. Just plug those values into this equation, and I've got so 0.741. So this has been computed successfully, right? Then let us focus on this term. What is this? So dou out one by dou net 01. That is this. What is the rate of change of out one with respect to net 01? What is this out? Activation function, right? What is activation function? Sigmoid. 1 by 1 plus e power minus x. So this is a sigmoid, the activation function. Now we are going to apply the partial derivative of the sigmoid function with respect to net 01. So dou out 1 by dou net 01. So when you apply the derivative for the sigmoid function, so if you say this is f of x, okay, the derivative of the sigmoid function is nothing but f of x into one function. So if you say this out, so out into 1 minus out. So this is sigmoid function. So there is a proof available. So probably you can go ahead and you can refer that. So out 01 into 1 minus out 01, just plug those values because I know this. What is out 01? So from the actual data, I can get to know this. So this is 0.1868. So this also I've computed successfully. This is done and this also done. Now we have to compute this. What is this? Dou net 01 by dou W5. That is this part. Compute this part. Now, so if you see what is net 01 here, the net 01 W5 outs H1. That means so this into output of H1, okay, W6 into output of H2, then bias 2. So that is what the net 01. Apply derivative with respect to W5. So when you apply that, so I've got out H1. That means only out H1 is impacting your net 0, 1. So that is 0.593. So take all these values, okay, the earlier value, so plug into this equation. So that is 0.74, 0.18, 0.593. So dou E total by dou W5 is this 0.082. So this value we have received 0.082. Now, what we have to do? After identifying at what rate the total error is going to be changed with respect to W5, then I know that how much this is responsible contributing to your total error. Then, so I can update this weight so that my error can to be reduced. How do we update this? We would use a gradient descent method. Gradient descent method we will use. What is the gradient descent method? So I have an objective function, for example, j of theta. Okay. So this is, it is a vector of function, okay, or j of w, let me put, okay, w naught, w1, w2, so and so. Now the first step in the gradient descent method is, so initialize these values randomly. Randomly you can select some values, randomly w naught, w1. So you can say, when I say randomly 0, you put 0, 0, 0, all of them. Then compute your error function, compute the error function. The next step is, we will compute the gradient for this error function, gradient of the error function. That gives us the idea in which direction we should move so that this error is minimized. Now we have computed the gradient. Now we are going to find out in which direction we should move so that the error is going to be minimized. That means I'm going to find out the new weight for this. The new weight is nothing but, so that is the current weight minus eta. Eta is a learning rate, and the gradient of whatever we have computed, the rate of change of the error function that we have computed. So this W5, I know this 0.40 here, okay, 0.40 minus neta. Neta is called as a learning rate. So let us set that up at 0.5, and this we already computed in the previous slide. So that is what you can see here. Okay. So this is basically comes from the gradient descent method. And this gradient descent method is a systematic way of reducing the error whatever you have here. Okay, 0.293. How we can reduce it? So it gives us the direction. It gives us the systematic way of reducing the error. Okay? And when you apply this method iteratively, now using this, so we have computed the new weights, that is 0.35. 0.35 is a new weight. Earlier is 0.40. Now we have successfully computed a new weight. So this results, definitely results in lower error so than whatever the current error we have. Okay, so that is W5 we have computed. Similarly, compute for W6, the same method you have to use, W7 and W8. Those values are here. So with these values, we have got 0.293 initial error rate. Now we are in the search of new weights. Those new weights should give us the lower error. So how do you get those new weights? This is a method. Whatever we have just discussed, this is a method that gives you definitely lower than this. How much lower? Yes, that is subjective to the learning rate, other techniques. Okay, but definitely it gives you lower than this. Now, after computing this, so here we'll mention those things. Now, once this layer is done, then we'll move to this W1, W2, W3, and W4. Now coming to this W1, now we are going to identify how much this W1 is affecting your total error. What is the rate of change of the total error with respect to W1? So again, the same chain rule. That is dou E total by dou out H1, out by net H1, dou net H1 by dou W1. That means this is directly so impacting your net, then out, then this is impacting. Out is impacting directly the total error. Then we are going to compute these one by one. The same method we are going to compute. So when you compute that one by one, okay, so do you total by dou W1, so I've got 0.0004. So update the weights, the W1, the same formula that we have discussed. The current weights, eta, this is a learning rate, do you total by dou W1. So I have got 0.149. This is my new weight. Earlier is 0.15. There is a slight change in that weight. So that is 0.149. Then compute for all other weights W1, W2, W3, and W4. That means, so we have successfully computed. So all of these weights, this as well as this, we have done it. Then, so once you compute this, yep, so once the weights are updated, then again send these data points 0.05, zero 0.5, zero point 0.1 inputs. So the original error was 0.2983. After the back propagation method, what is a back propagation? Whatever the procedure that we have done, that is called as back propagation. That means based on the error that we had here, so we are so identifying, we are going back to the network, we are going to identify what are the best, the weights so that the error would be minimized. So that is what the back propagation method. Right? So this back propagation method, we have updated our weights, and with that, the new weights, so we have got the error 0.291. So if you see the difference, this might be very, very low. The small difference is there, but this is only one step. So like that, whatever you have done, you have to do multiple times. How many number of times you have to do? Let's say 10,000 times we have done this exercise, going feed forward, back propagation, again feed forward, back propagation, identify the weights, update the weights, again send the data. So like that, we have done 10,000 times. Then the error so has been reduced to 0.000035. The error has been reduced. That means the weights have been optimized. So this procedure is called as back propagation method. Okay? The multi-layer perceptron back propagation method. Right? Now, let me take the questions here. Yeah. First question is how do you fix the initial weights? So initial weights we can fix using uh, a distributions. Randomly we can fix. First one is randomly we can fix. Second one is you can take these weights from a distribution, from a normal distribution or from a uniform distribution, any other distribution, but more generally we'll take uniform or normal distribution, the weights. So you can mention that, okay, the weights should come from this kind of a distribution. That's how we can uh, get the weights, initial weights. So how do we know that which activation function is suitable for our model? Right. See, there are a few things called as hyperparameters. Okay. So let me go through that. Yeah. These are called as hyperparameters. Let me discuss about those things. So how do you know that? How do so one know that how many number of hidden layers have to be used? If you talk about this, for example, if you're talking about this, how do you know that we have to use only 3 neurons in this hidden layer? How do you know that only 2 neurons have to be used in this hidden layer? First of all, how do you know that only 2 hidden layers have to be used? Those are called as hyperparameter tuning of the network. And these have to be determined empirically. What do you mean by empirically? You have to test it out. There is no definite answer for this. Try with 10 hidden layers, try with 5 neurons, different combinations, right? And just check how much the error that you are going to get. And also, how do you know that which activation function to be used? Again, test it. So use ReLU, use ELU, use leaky ReLU, use sigmoid. Different activation functions are there. Use these things and test out which one works for you for a given data set. Error function or loss functions. So we have MSC, RMSC, we have different loss functions. Just check with those things also. And gradient descent method. We have a different gradient descent methods. So 3 kinds. The variants of the gradient descent methods are batch, mini batch, and we have stochastic gradient descent. These are all the different methods. The batch gradient descent is all the data points we would send through the network at once. If you have 1 lakh data points are there, all the data points would be sent to the network so that the network can compute the error and use and then back propagation and update the weights. Mini batch is basically, instead of sending all of these data points, just send chunks in chunks. Let's say, for example, so 1,000 data points at one go. Send through the network, update the weights, and again send next 1,000, next 1,000. That is mini batch. Then stochastic gradient descent is send only one data point at a time to the network and update the weights one data point at a time. So these are the different variants of the gradient descent method. And again, so these are called as hyperparameter tuning, and we have to identify empirically. And also learning rate, that is neta. This also we have to identify empirically. This would be between 0 to 1. Right. So few more questions. Is there any flexibility to define new activation function? Yes, yes. So you can define your own activation function. Yes. All right. Now let me show you how do we build this in Python and how do we fine tune the network and how do we identify uh, which activation function is going to work well and which the initialization of the W, the weights, so is going to be work well for a given data set. Okay. So let me open Python now. Yeah, let me connect this Google Collaboratory. Right. Okay. Let me upload the data here. So divide the data into the independent variables and different variable. So apply the standardization. Yes. Let us see this standardized data. So always, so it is recommended to apply the standardization when you're building the neural network. So because neural network are very easy to overfit the data. Right. Now, so what we're going to do is we are going to identify something called as batch size and epochs in the neural network. Okay. What is a batch size? So there are few things actually we need to understand the batch size, okay, and the iterations and epochs. So we have three key terms in the neural network. One is so the batch size. So we have iterations and epochs. So people might think that iterations and epochs so are same are similar. No, it is not same. Let's say I have 1,000 data points. So batch size equal to 500 means every time the 500 data points would go through the network and update the weights. And to cover the 1,000 data points with this batch size, how many iterations I need? Two iterations I need. So with these two iterations, I have completed all the data points. That means all the data points have been exposed to the network. Then that is called as one epoch. That means how many number of times the network gets the entire data set, that is called as epochs. Epochs, right? So let's say, for example, if I say two epochs, that means there are four iterations and two times these 1,000 data points so sent to the network. So that is the difference between the batch size, iterations, and epochs. And let us identify what is the best batch size. Should I go for the 500? Should I go for the 300? Or what is the best batch size? And how many number of times I have to send this data set to the network. Let us find out that. So here, just set up the import the libraries. Just build a function, a custom function. So that gives us the network idea here. So we are going to use Keras. Okay? And so internally, the Keras uses TensorFlow. You can see here TF means TensorFlow. The Keras is a wrapper around the TensorFlow and sequential, and we are adding the layers. So you see here dense. Dense means neural network with the 12 neurons. Dense again one more layer we are going to use with the 8 neurons, and here we have output layer. So if I have to give you the pictorial representation of this, so this is what you are going to see. So we have the input layer, so that here we are not showing. Then we have the first hidden layer. In this we have 12 neurons. Total 12 neurons here we have. First hidden layer, then the second hidden layer with 8 neurons, the second hidden layer. Then the output layer, that is 1 neuron. So this is what actually this structure, this coding means, right? Right. And then we are using initializer. Kernel initializer is uniform. That means the weights, initially the weights have to be updated or taken from the uniform distribution for this, whatever the value that you get here. And from here, so here also we are using uniform, this from the uniform distribution we are going to get, and here also we are going to get uniform distribution. These are the weights initializers, right? Let us create this function. So here we are going to discuss, we are going to identify the batch size. So here we have given 10 data points, 20 data points, 40 data points at a time, and epochs are 10, 50, 100. Now I want to find out what is the best batch size and what is the best epochs. Okay, so the network would evaluate all the combinations of this batch size as epochs and gives us the best combination. Okay, let us build that. Takes a minute or two. Still it is running. Okay. Yeah. So it ran successfully. Good. And let us see the best combination. So the best combination is a batch size is 10. number of epochs are 10. So with this, we have got the best accuracy, that is 76. Again, the 10 and 10, right? So there are infinite number of possibilities are there. So if you have time, if you have resources, probably you can check the different batch sizes as well as epochs. So far, whatever the combination that we have given, so these two are the best combinations. Fine. Then learning rate and dropout rate. So the dropout is basically we will use for the regularization method. That means if at all the neural network is overfit, okay, what we do is we would remove some of the neurons from the network. That means we will disconnect the neurons from the network. So that is called as dropout. And how much percentage of the neurons have to be dropped out from the network is called as dropout rate. The learning rate is nothing but eta. Okay. So let us find out that as well. So we have given learning rate 0.001, 0.01, zero 0.01, 0.1, and dropout rate is this. Okay. Now, so once we test it, let us find out what is the best combination. Right. Now the best combination is this. 76 is the accuracy of the model. Dropout rate is 0. That means we should not apply any regularization method. The learning rate is 0.01. Okay, so these are best learning rate. So out of all these learning rates that we have given. Then the activation function. Okay, activation function, kernel initializers. So we have three initializers. So the mostly we'll use normal, okay, and uniform and zeros. So let us find out that which is the best initialization method as well as activation function. So we are testing softmax, relu, tanh, linear. These are the activation functions we are testing, and these are the uniform. These are the initializers, the weight initializers. Let us test these things. So it is taking all the combinations. You can see here linear normal, then linear zero. Right? Yeah. So it has been done successfully. Now you can see the best is 76% the accuracy. Activation function is linear is the best one, and the initialization the weights initializer are normal. From the normal distribution, we have to take these are best one. Then the number of neurons in the activation layer. How many number of neurons we should use? So we are going to test for two layers. So in the first layer, so we want to test for whether we should go for the 4 neurons, 8 neurons, or 16 neurons. The layer 2, 2, 4, 8, which is the best combination. So in the network, let us go for that. Right. Then let us find out this. So we should use in the first layer 16 neurons. In second layer, we should use 8 neurons. So this is 76% is the accuracy. Now, so let us collect all of these, the best parameters. Let us use in this. So we are going to use all of these, the best parameters in this network, and we are going to build this network. And with that, let us find out what is the best accuracy here. The best accuracy that we have got with the best parameters is 78%. Okay. But here, what I've done is I've used the searching of the best parameters, hyperparameters, bits and pieces. That means two hyperparameters at a time. So I try to find out. But ideally, what you have to do is you have to put them into one network like this. What is the best batch size? What is the best epochs, learning rate, dropout rate, activation functions, right? And initializers and neurons. So at a time, all of them you have to test it because the network would identify the best combination searching through this space it gives us. But what we have done is because of the computational complexity, I've not included all of them in one network. Okay? So it takes, if you include all of them in one network, it takes good no, half a day. Minimum half a day it takes to run. It gives you the best hyperparameters. Right? So if you have time, for example, tomorrow or day after tomorrow, what you can do is you can run this. So on this Google app and just start running and leave it. And so after running completely, you can see that. So this is the way to find out the best parameter, hyperparameters. Yeah. Right. So this is the neural network and backpropagation method. So any questions? So any clarifications required? Right. So ADAM is basically adaptive momentum. Yeah, that is optimization algorithm. So that is slightly deviates our the content basically. But anyway, we are going to use that as part of our the optimization algorithm in this adaptive momentum. Yeah, that we are not going to cover as part of this here. Okay. Let me give you momentum first. Okay. Quickly, I'll give you a few more aspects of this. Then we can. Let's say, for example, I have yeah, I have my error function or the function surface is like this. This is flat. So this is my the function surface. Let's say, for example, now using this gradient descent method. Okay. So when you apply this, so initially we are here, for example, you can think of this as a ball. So then ball will so just roll out here, okay, here and here. So one step by step. Okay. So then comes down here. Then the moment it reaches here, since this is a flat surface, the gradient will be zero. Then the algorithm thinks that we have reached the local optimum. That means this is the minimum value that we have okay, so achieved. And if you move this side, there is no change at all in the weights or the gradients. If you move this side, there is no change at all. Then what we do is, so in this case, we have not achieved actually the optimum level, right? So optimum level is here. So this is what actually error you can say. So the algorithm thinks that hey, this is optimal level. It stops here, but there is optimal here actually. This is not the optimal level. What we do is we'll have something called as momentum. Okay, momentum. So what momentum does is, so we'll add a little value to the gradient to push this ball roll. Okay, so just we'll push this ball towards this. Then the ball comes here. That means the next step would be here. Then after that, it picks up the momentum again. It drops here. Okay? The little push, whatever we give, so that is basically we'll call it as momentum. We'll add momentum to the algorithm. Right? So these different features are available in the different algorithms. Like we have ADAM, the adaptive momentum. We have ADA delta. We have ADA grad. We have RMS prop. Yeah, all of there are different optimizations available. So the best combination is I can think of Adam optimizer. So place the momentum, or we have something called as Nastro momentum. So with the activation function, these are the best practices with activation function of ReLU. So first you can try with this. Okay, if it is not going to work out, then you can probably can search, go with other options and apply a regularization parameter, that is dropout. Yeah. So that's what actually you can try it out first. Then you can go for the next other the options, and you can try it out and you can check with accuracies. Okay. Yeah. One important thing I would like to announce here. So it is important to us, not for you guys. Yeah. Uh, oh, it is about the feedback, guys. The overall feedback. Let me open. So if you think that this is good for you and you have learned something out of these sessions, I would request you to give us the review. Okay, let me open this. So our team, we are going to post this link. Okay. So in the chat window, and also our team is reaching out to you for the review. So if you think that this is good, okay, you have learned something new and this is good course for you, then you can give 5-star rating for us. And also you can write something here. So I have, okay, learned data science, so from ExcelR, okay, and it is quite good. So if you feel that, okay, it is up to the mark, and if you think that these are good, okay, something like that you can write, and you can give us the rating as well, and you can just post it. Okay. And so please give us the rating, and Mukesh would post this link to you. So Mukesh, can you please post the chat window, and also our team will reach out to you separately. So for the review. Yeah. So please give us the rating. Right. The certificates. Yes. We are going to circulate the certificates. So we have to discuss with the SRM, the college faculty members as well, the coordinators, and so we are going to circulate the certificates to all the people, all the students who have joined these sessions. Yeah, don't worry about the certificates. And we have, yeah, so we have given all these the material, in the sense the codes as well as the data science we have uploaded in the Google Drive. And the material, yeah, so material, so you can access from our LMS. We are going to send you the credentials for our LMS, and you can view them. Okay, you cannot download because these are the copyrighted material. You can view them as long as you want. Okay, yeah. So drive link, I think that has been already posted in mm, the app, right? Yeah. Mukesh, you have already posted, right? Yeah, yeah. So the drive link, yeah. So drive link already been posted in the Telegram app. So once again, we'll post it, and you can. Yeah, yeah, we are working out on the Dr. Banaut, okay, Sitaramulu. So you will get that. Yeah. So you will get that email with the credentials, and you can view the lecture, the material, the PPTs, and the videos, right? So the videos are available in the YouTube. So those you can access. So we are not going to remove them. You can access them. Yeah. So as I mentioned, certificates. So we are going to send you. Anyway, you are going to give the feedback on daily basis, right? So that is what actual attendance, right? So we are going to give you all the students who have attended. Yeah. Yeah. Once you click on that, so you have to wait for a few seconds. Okay. So 3 to 4 seconds. Then you can select the stars. So if you see, for example, just wait for a few seconds. Right. So then you can see the stars and you can give that star rating. The implementation code, yes. So I have we are going to give you that. That is already available in the Google Drive. And the slides, no, we cannot give you that because of the copyrighted material, but you can view the slides. So we are going to give you the access to our LMS, and in that you can view all these slides, whatever we have covered so far, and that you can view as long as you want, basically. Yeah. So yeah, thank you guys. Thanks for the feedback. So I should also thank you for patiently listening all these days. It's great, actually, great journey. So if you have any questions, you can directly post the questions in the Telegram app, or you can also reach out to our support team. So we'll get in touch with you guys. Yeah, yeah. We are also planning to conduct artificial intelligence and deep learning, which are completely uh, the neural network based the course. Yes. So shortly we are going to announce that as well. Yeah, a series of lectures actually we are planning to conduct. One is on the NLP, okay, and chatbots, and also we are going to conduct the sessions on AI, completely the deep learning sessions. Yeah, you would hear more from us. So from the month of Jan, we are going to uh, circulate the schedules for all these sessions. Yeah, unmissed attendance in early days, 1 or 2 days, that's okay. So if you have given the attendance at least a week, then that's fine, no problem. Okay, anyway, so the cutoff would be decided again with the in a discussion with the SRM team. Yeah, yeah, sure, definitely. If you want to conduct some more sessions, okay, uh, from the Ramaya Institute of Technology, yes. Could you please post your mobile number to me, Pushpa, directly, so that I'll give it to the relevant teams so they'll get in touch with you. Right. So if you want to conduct similar kind of sessions for your college, yeah, definitely. So we'll come forward and we'll conduct these sessions. Mukesh, please make a note of these numbers. So we'll contact them and we'll get the requirements. So these numbers, if you, yeah, so if you really want us to conduct some sessions for your college, yeah, that's where actually I asked you to post the mobile numbers. It is not for the certificates, guys. It's only if you have any requirement to conduct the sessions in your college, yes. So that is where actually I asked. Yeah, today's link has been posted already for attendance. Yeah, yeah. Sure, sir will contact you. Yeah, Mukesh, please note down those numbers. Okay. Okay. So thank you all. So that's all from my side today. And yeah, so thanks for joining and so patiently listening to me all these days. So it was great interacting with you. So all the best, all the very best for your future.